Okay, so this is the first of two videos where I'm going to give you examples of how to apply Hess's law, okay, using different enthalpy change values that you've been given. Now, 9 times out of 10, you'll be given an equation. Other times, maybe you'll be asked to write the equation for a reaction, but we've been over that, and you should be able to set up a balanced equation like so here. And what we've actually got here is for the burning of methane in oxygen to produce carbon dioxide and water. Okay, so let's say we actually can't in a lab calculate this delta HR here, okay, this enthalpy. And in fact, it's an enthalpy of combustion equation for methane when you look at it. Okay, so this is basically enthalpy of combustion of methane, or it could be any reaction, delta HR. Now, you may be given the enthalpy of formation, okay, and I should put a little theta there, for the different reactants and products that you have. So you'll be given some information like this here, okay? And what you need to do is use this information to find delta HR. So rule number 1, okay, which is on your worksheet, when you're given delta HFs for a Hess's law energy cycle, your intermediates at the bottom down here, okay, must be the constituent elements of your reactants and products. So in this case, we have a carbon, we have 4 oxygen atoms, and we have 4 hydrogen atoms, okay? So you know what, you don't need to balance this down here. I'm just putting them in so we know exactly what we've got. And of course, because it's balanced, whatever we've got in our reactants, we've got in our products. So it's a link between the two, okay? All these are made of these, and all these are made of these. Now, if you remember, your delta HF definition is the formation of 1 mole of a substance from its constituent elements. So when you're given delta HFs, you put your constituent elements at the bottom, and then you put an arrow in to show the formation of those different substances. So we are forming delta HF for CH4 for methane. We are forming methane, so this arrow goes here, and we can put in the value, I'll put these in a different colour, of minus 74.4. Okay, so that's our enthalpy of formation of methane. Enthalpy of formation of oxygen, well, here it's listed as 0. That's because the enthalpy change of formation for any element is 0. I mean, forming oxygen from oxygen, well, you can't put a number on that, okay, because oxygen is already in its standard state. So this is 0. We can forget about this one. So any element, delta HF, is 0. Okay, so don't panic if they don't give you information for that. It's because they're assuming that you know it's 0. Now on to carbon dioxide. We are forming carbon dioxide from our constituent elements, and that number there, I'll put that in red as well, is minus 393.5 kilojoules per mole. Now, of course, we've got water on the end, forming water, which is minus 285.8 kilojoules per mole. Okay, so rule number 1, constituent elements at the bottom. Rule number 2, arrows up. Okay, because we are forming all of these substances. Third rule you should follow, okay, and final one in terms of setting this up, is you must take into account the number of moles that are balanced in the equation. Okay, this is 1 mole, so that's fine. This is 0, even though it's 2 there, but it doesn't matter because 2 times 0 is 0. 1 mole of carbon dioxide, we have 2 moles of water. So this must be 2 times minus 285.8. Okay. Now, once we've set this up, taking into account the direction of the arrows, okay, and putting our numbers in like so, we need to think about putting these together to find delta HR. Now, you might be shown a slightly different way in school or college, that's fine, but this is the more clear-cut way, I think, of working these out. What we need to do is get from here to here. Now, for example, like so. Okay, we need to go this way. Now what you'll notice is that some of these arrows, these two in fact, are going the wrong way. Okay, we don't want to form methane, we want to split methane up into its constituent elements so we can then form our products over here. So in fact, these, in terms of conservation of energy, when methane is formed, it releases negative 74.4 kilojoules per mole. We actually require to put in 74.4 kilojoules per mole to split it and form these. So what you've got to look for now are arrows that are in the wrong direction. We can ignore this because it's 0 anyway. Okay. So what we need to do is reverse or invert this value here for any arrows that are going the wrong way. These are going the right way, so we can leave these numbers as they are. So if you remember in Hess's law, the sum of these equals the delta H for that reaction. Okay, so delta HR for our reaction at the top equals not minus 74, we are reversing this, we are inverting that number, so it's actually plus 74.4, positive 74.4, plus minus 393.5, plus 2 times minus 285.8. Okay, now I've kept the pluses in there because it is the sum of these, okay? But once we take into account these negative numbers, we can easily write it out like so. So we know that's just 74.4. And then plus minus, well, that's just minus 393.5. And then plus minus again, so that's basically minus 2 times 285.8. And what we should get is minus 890.7 kilojoules per mole. Okay, so that's how you work these out using delta HF. Very quickly, the headlines. Balanced equation at the top, states of matter, very, very important. Okay, you get given your list of delta H formations, you put your intermediate elements at the bottom, okay, your constituent elements, and then you put in your numbers for the formation of each of your reactants and products. Arrows up, ladies and gentlemen. Okay, put your numbers in, taking into account the number of balanced moles in your equation, and then put them into here, taking into account finally the direction of your arrows. Okay, so that's how to calculate delta HF calculate delta HR using delta HF values. The next video, I'm going to go through an example of how to use enthalpy of combustion to actually find the delta HR for a reaction.